I'm Philipp. I run our developer relations team. I've been with Elastic more than 8 years, so you can try to ask me ancient history or the newest stuff happening. I'm happy to answer that. Before we dive into that, I'm always asking a trick question to wake you up. This is my Twitter, Mastodon, GitHub, whatever handle, and it has something to do with my last name. How are the two connected? And most of you are old enough to know this.
It's a ROT 13.
It's a ROT 13, exactly.
Yeah, exactly.
Very well done. I know my audience, like the young folks don't know this anymore, but those who have been around for some years have seen the infamous ROT 13. So yes, that is where you can find me online. Okay, so let's dive in on the tech side. So Elasticsearch, for those who have never heard it, is a distributed, now again, open source, RESTful search engine. It is very strong on the clustering side. That's kind of like where it started off, like back in 2010 when Shai, our founder, started that. I always picture him in his bedroom starting to write the code. And I actually asked my first Elasticsearch question in December of 2010 when I was a user, which was a very bad question, so don't try to look that up. It didn't make much sense. But we've come a long way since then. And it initially tried to solve the text lexical search problem. And it has since then evolved into the other solutions, but also now with AI and generative AI and vector search, we're in a much broader scope that we have developed in. Elasticsearch is built on Apache Lucene. We're very heavy contributors to that. So Lucene is basically the thing that stores data on disk and makes it available for search. And Elasticsearch is then the query DSL, the REST API, the distribution and replication around that. And there are many improvements and features under the hood. We can dive into a couple of those over time. So when we look at search or what a typical document is, we'll start off with a bar example. So we have a bar that has a name and then a rating and a description, and maybe we have a dense vector representation of that description and the location and all of these things. And all of these matter for search, that you actually find what is useful.
JSON?
Yes, we are a REST API, so JSON is what we take in. For love it or hate it, that's the format that we started with. The important thing here from our perspective, besides taking in JSON, is that these are all the different data types and formats that we support. And all of those are relevant to make your search better. For example, when I'm looking for a bar, I might look for some that are highly rated, or I'm looking for some specific description. But I probably also want to have a geo search and say, like, give me the bars within 5 miles or 20 miles or whatever, but not across the country. You might have, like, do they have a specific head chef or bartender or whatever else? Like, you want all of that data, and that is really the strength that Elasticsearch is giving you, that all of these different types of data are combinable, and you can work with all of them to make your search more powerful and expressive. That is the core of why a search engine is so specific and different. And this is, by the way, what a traditional database will struggle to do, to combine all of these things and then also have this relevance aspect to give you the most relevant aspects. Because you might have a combination to show you results to say, like, I want to have a combination of the rating, the distance, and maybe the type of bar. And then to give you the most relevant results based on a combination of these. To just make relevance a core concept of your results. Whereas traditional databases are very much black and white. You define a condition, everything comes back in that condition. You maybe sort on one specific column, but you don't have like this relevance concept that we are diving into here. And then there is, for vector search, which is the main focus of this talk, there is the data structure behind it. There are multiple ones. One of the most widely used one is HNSW, or Hierarchical Navigable Small Worlds, which is a horrible name that I can never properly pronounce, but I'll stick to HNSW. How it generally works, I hope I'm not moving too much, but I'll try to move over here to show this. What we're looking for is this blue dot that is somewhere here. And how HNSW works is, or let's take a step back. If I do vector search, doing a brute force of combining all the representations with millions of documents is very expensive because you basically need to do millions of vector comparisons. What HNSW is doing is basically it's like an approximation to get closer to it. You go through multiple layers. Each layer adds more data points, and basically in each layer, you try to get as close as possible to where you want to go. So here you only have basically 2 data points, and to get closer to this one is the closest one. So this is where you go, and you only have like a handful of combinations or comparisons to do. And then you go down a layer where you have more data points, and here you move even closer to where you want to go. And then you go down to the next layer, and then you only have basically to do the comparisons in this sector here, rather than comparing all of the documents against each other. So this is an approximation. It will be very close normally, but it avoids having potentially millions of comparisons to do, and will reduce those to a couple of hundred or thousand comparisons and make this much faster and computationally feasible to give you results in a reasonable time without doing an exhaustive search.
So I'm familiar with other vector databases also offering IV flat indexes. Is that similar to this? Operate similar to this?
It is solving the same problem. It's a different algorithm. This one is very good for, so that the trade-off is HNSW has these random access. So it is really good for, or it's primarily good for if it fits into memory. The HNSW structure needs to fit into memory. The one that you mentioned is more friendly to disk space, but has different performance trade-offs otherwise. But for fast search, HNSW is pretty much the standard what people want to, or what most data stores are using. Right now, we don't, or HNSW is the only one that we have today. We will see if we add others that are more disk space friendly. But since we're focused on fast search results, HNSW is kind of the natural fit there. And by the way, please stop me at any point in time if you have questions. I'm always happy to go left or right. So let's dive into core capabilities of vector database, or what we have been doing. So Elasticsearch has supported dense vector, which is kind of like the data structure for all of this, for around 4 years or so. 2 years ago, we added that approximation with HNSW. Before, you could only do this brute force comparison across all of them, which worked fine if you had a set of like 10,000 or so documents to compare against each other. But to do more, you need that approximation with HNSW, and that was added approximately 2 years ago. And since then, there have been various improvements over time to make that even better. And we also have added more vector compression to reduce that memory requirement, because the main downside of HNSW is that it's costing you a lot of money in terms of memory. And we'll get into some of those optimizations as we go further through the slides. But that is kind of like the main progression around that dense vector search we have in Elasticsearch.
Is the compression associated with the vector data or the vector index?
So we're talking
both,
about the HNSW data structure in memory. You can basically imagine it like a 2-dimensional space, more or less. So you have one dimension. Let's say this is our 2-dimensional space, since I don't have a whiteboard. One is the number of vector dimensions. And you might have, for each document that you might have 384 dimensions or 1,500. So this is this dimension. And then the other dimension is basically the precision for each single dimension. And the default is normally float, which would mean 4 bytes. So if you have 1,500 dimensions and it's 4 bytes, you need 6 kilobytes of memory for each single document. If you have 1 million documents, that will be a good amount of memory. Now, the 2 tricks that you can play with this, you can either change the precision here. So rather than doing float with 4 bytes, you could do byte
half-fact or something,
or half byte. And we support both. And we'll get into that and how you can optimize those. But that is kind of like, so the memory requirement is basically the surface of this square. And so you can either reduce this dimension. The other thing that we're currently working on is reducing, when you insert the data, the number of dimensions dynamically. So you can also squeeze it from the other side. There's a very fancy and new paper which is called RabbitQ, for bit in it. And that is going into that, like reducing that dimensionality. Which is, by the way, a good point, that if you pick the model, because the model that you pick defines how many dimensions you need. If you can find a model that works well for you, that has fewer dimensions, pick that, because it will just be much cheaper. You might have a use case where you need more dimensions, but it will cost you in memory. But it's a great point. So the high-level overview of how vector search in general works. You have data coming in, and one of the big advantages of vector search is that it's not just based on text anymore. You can also do text, but you can also search images or audio or video or whatever else you have. Because it's not a textual representation that you have, but you have a vector representation. So you basically have an array or dictionary or whatever it's called in your programming language of choice of these, by default, mostly float values, defining those 1,500 dimensions or whatever. And that should give a good representation of that document. And so whatever document type comes in to create through a so-called inference step or pipeline, you create that vector representation, this array of many floating values. This is what you store. Your query coming in on the other side goes through the same process and also creates this large array of vector representations. And what you then do is you compare which vector is closest, so this vector you're searching for, how close are they to the documents that you have stored. So the similarity here is really based on the space in vectors. And you have multiple algorithms to compare that. Cosine, probably the most obvious one that everybody has done in school, that you have like cosine similarity, and then you find what is close. And that is the result that you get out. So rather than having a keyword-based search, which is the traditional way, you have this vector representation. And it could, for example, you could even search, some models support that you search for a string like mountains with a lake in front. And maybe you have a model that can actually encode that from an image. So Clip from OpenAI is a very common example, which has the nice attribute that it can like index images, but also text. And so you can search your images just from text. It doesn't have just to be a similar image, but you can really just type in what you want to find in an image. So that's the big feature here of vector search, is that it is not limited to text, and it's also not limited to vocabulary mismatch, because it really, depending on your model, it tries to extract the meaning from what you have, rather than just having this string-based lexical matching. That is really the core of what vector search is trying to do. And to make this maybe a bit more concrete with some API calls, and we'll get into a demo on that later. So that data type that we have in Elasticsearch is represented by HNSW is called dense vector, because we also have something that is a sparse vector. We have our document. Now we have like Snow Crash from Neil Stevenson, and it was released in '92. And you have a description. And the description also has this vector representation. And we have multiple books. And you can see here the first one has just one description, like with one model. Maybe you want to use different models because they have different strengths to find something that is similar. So here we are taking that one description, and this is the representation by the model 1, whatever we're using here, or the model 2. So you can have multiple vector representations. Of course, you will pay the price, those to create the vector representation and to keep it in memory and store it on disk. But you have the option in Elasticsearch to have, for one field or for different fields, you can have multiple vector representations for any field you want.
And you create indexes for each of those separate representations? So
the index, it's kind of tricky, because index in the relational world is what is normally a B-tree index, whereas in Elasticsearch we call this is basically a collection of related documents. It's all table in the relational world. It doesn't quite compare, but it's more closer to the concept, or MongoDB would call it a collection. It's a collection of related documents. So when I say index, I'm sorry if that causes confusion. It's a collection of related documents. So books is the index here, where we store those different documents. And then we have those different fields with the representation of whatever we have for each field. Does that make sense? Or
no, but that's okay. I think I'm there.
It has some limitations. That's why I'm cautious not to call books a table. But in the relational world, this is kind of like the similar concept. So you have, this is the table, and these are the columns that you have. It's just not quite the same, because we have JSON, which is semi-structured. So it's not as rigorous as a table structure. But that's kind of close enough for the representation. And then you can have for each field or column, you could have this vector representation if you want to. And you can also have more than one vector representation for a field, because sometimes your fields are very long, and like the vector is quite expressive, but it's still a compressed representation of the data. So you might do something called chunking, where you break up a very long text into multiple chunks, and each one gets its own vector representation, just to target that specific area. And then you will have multiple arrays of these dense vectors, or multiple dense vectors for a single description field. But all of that you can do here in Elasticsearch and combine as needed and what makes sense. So you have a lot of options, and you can dive into that as much as you need. What the output in a more realistic example would then look like is you could provide a search. So here I'm searching the index example index or table. Underscore search is the endpoint that I'm searching. And then I could say, like, find me, based on this vector representation here, find me the closest documents. Do you want to write queries like that?
No.
No. Ideally not. It was the first step of how you could do that. Nowadays, we have made it a bit simpler, where you can say, we have a model that we can run within our stack. For example, here, mini-LM is common model. And here we are saying, I want to run my search, and I want to use the text the opposite of blue, and it will automatically translate that to the vector representation and run the query for you. So you don't have to paste in that big request. I mean, probably your programming language is going to do that, but this is much more manageable to actually query it. If you stored the text, we have something called an ingest pipeline, where you basically run your documents through that pipeline when you store it. It will create the vector representation and store it with your documents. So you don't have to really think about it or touch it. You just set it up. You throw the documents without the vector representation at the API, and it will create the vectors for you and store that.
What is it using to do that vector creation?
So the model here, you can, so from, for example, from Hugging Face. Yeah, no, that's a totally valid question. So you can pick most of the models from Hugging Face, for example. We have 2 built into our stack as well that are there by default that we think are a good choice for many. But you can pick any PyTorch model from Hugging Face. You could import into our stack and run it from there. We also nowadays have what we call the inference API, where you could reach out to external services. So, for example, OpenAI, Amazon Bedrock, Cohere. We integrate into a lot of these. So you then only need to call Elasticsearch, and behind the scenes, you can configure that inference step. And then Elasticsearch will forward your string to, let's say, OpenAI, get back the vector representation and store that for you. But you don't need to do the extra API call.
Okay. But you could, in theory, you could you could train your own model based on your own native, I don't know, you have particular data needs, or you want something that inferences particularly well in that problem domain. You could do that and then use that with Elasticsearch. And like, you just have the data scientists over here create a model for you, and you just go, great, plug it in and use it. And if they generate a new one, you can swap it out for a brand new one.
So swapping out this search and swapping out is always dangerous, because like if you have like done the inference with one model and then you change the model,
you'll have
I'm
to
not sure the search result will actually be that good. So you might have to re-ingest all the documents with the new model. Otherwise, this might break. But yes, and you can either run this. We can run that in the stack for you. If you give us a PyTorch model, we have a command line tool called eland that can import your own PyTorch model into our stack and run it there. Or you could, of course, run that yourself wherever you want, maybe on Llama or whatever other infrastructure you have for running a large language model or an inference model. Do that in your programming language and just give the dense vector representation to us.
Right.
That's really up to you how you prefer that. We try to give you the feature for convenience, but nothing forces you. You can just give us the dense vector representation and do the rest however and wherever you want.
And I think one of the things I see in this is just a JSON document store, and I can put, it's essentially just a list of numbers. That's what the dense vector is, a list of numbers, and I can populate it myself, or I can have the platform populate it for me.
Yes.
I think really key in there is if you change the algorithm, you're just going to have another dense vector that you store with a new algorithm, so that your old search results that use the old algorithm aren't invalid, but maybe you'll get better search out of the new algorithm.
Yes.
So that multiple embeddings on the same root data is incredibly cool.
Would that run? You'll run into storage issues, but I'm trying to remember where. Will they be memory storage issues? Because
normally memory will be the much bigger constraint.
Yep.
Because so you will need more disk than memory, but memory is just so much rarer and more expensive than disk. That disk is, for vector search, normally not the limiting factor. It's really memory that will squeeze you. And we, by the way, I have a slide later for that. We have, for our cloud service, for example, we have a dedicated instance type for that, which has less disk and more memory, just to play into that, because otherwise you're killing yourself. And of course, you can have as many representations as you want. You just need to pay the price.
Yeah. And I think getting back towards the question that Ray was adding about indices it has a different meaning in a document database to a relational, but it's about how you get to that search, that small world search. That's generating those small worlds is the bits that's the equivalent of the index.
Yes. So that the problem is, so index is a very overloaded term in the Elasticsearch world. So index is the collection of documents. It's also what we call the operation to store it. We don't call it store, because there is this full ingestion process that also happens for lexical or keyword-based search. That's why we call it to index a document and not just to store a document. And by default, every field in Elasticsearch is indexed or has an index structure, which is a bit different than in a relational world where you always define, like, this is my B tree, or this combination of fields should be a B tree. Whereas in Elasticsearch, by default, everything is indexed. You can change that and turn it off because, of course, there's an overhead. But by default, everything is indexed for you. Kind of like a bit of a mind shift.
First, because you come from a textual search world where any word could potentially be something you could search against, right?
Yes.
Yeah.
So it's a great feature. It's also great for demos. If you have a lot of data, you just need to think, like, what do you actually need and use? Otherwise, you're going to pay for something that you don't need.
Right.
Which always pains us a bit when we're like, you have all the options, but you need to use them right. And it pains us when somebody just doesn't care about it and just stores everything. And then says, like, oh, this is very expensive or heavy. And we're like, well, you have the convenience, but you need to use your powers right.
And you mentioned that memory was a critical resource
for dense vector search, especially. I mean, in general, so the way that Elasticsearch works is it's a Java application, so it has the heap and off-heap memory, and the off-heap is normally caching from the file system. So the more caching you have, the faster your queries will be. But for dense vectors, it's especially critical because the HNSW data structure has so much random access that doing it from disk is very slow. So you will get very poor results if your HNSW does not fit into memory, much more than other data types that we support. That is the downside, but that is a general downside of the HNSW algorithm or approach. The other thing that is important, and this is especially where some of our competitors fall short, is that you want to not only have vector search, but you also want to combine it, for example, with filters. So for example, here we're saying, like, I have a range filter for everything between, or 1 month ago from now, and in a specific subcategory. And I only want to do my dense vector search on that. So you want to have these traditional filters, so you want to be able to combine it with a longitude and latitude. And here, this is maybe more a European approach for 200 kilometers. But you want to have these different options to limit your data set. And it's not just about, like, similarity in a dense vector sense, but really about reducing the data set to what is relevant and combining all those search features, and not just having vector search of its own. I don't want to say the holy grail because that might oversell it, but what generally works very well is if you combine keyword search and vector search into hybrid search together. Why is that the case? So that Keyword search is what we're all very used to. And your users normally get pretty upset when they know that the word exists in your documents, but you don't find it. And the problem is vector search is much better about like similarity and the concepts or the general direction rather than this exact match. So you often want to have this combination. You want to find exactly the words that or the keywords that your users put down, but you might not want to be limited to them because otherwise you need to have query rewriting and synonyms just to rephrase something. So keyword search gives you that exact match that people oftentimes expect, but it doesn't limit you that somebody needs to remember exactly how something might appear in your data set, but they can more describe the concept and still find it. And combining those two often gives you the best result. How you combine them, you have two different options. You can either manually boost them. So there is each search method basically has a so-called score, like the relevance for each search method. And you can then just add it up or combine it. But what is a very clever algorithm, and there's also a nice paper around it, is called RRF, which stands for Reciprocal Rank Fusion. It's basically blending the positions in different searches together. It's not just limit or going for this numeric score, but it's really looking at the positions. Like let's say we have a dense vector search, a sparse vector search, and a keyword search. And it looks like document N is in position 3 here, 5 here, and 1 there. And it blends those positions together to give you an overall position. Has a very simple calculation. It's basically they statistically figured out that 60 is a good value for that calculation is 1 divided by 60. This is this default value that works out well, plus the position where it's in this specific search type. You form the sum over all the search types that you have. That gives you the numeric value, and that sorts your documents. And that works very well across different search approaches. Based on actually, this is a very nice paper because it's only like 2 or 3 pages. It's very readable. And it gives you good search results to combine different search approaches together. I mentioned the built-in models. Like we have 2 models. One is a sparse vector representation, and that will make more sense when I show you. And then we have a dense vector representation, E5. E5 is very good for multilingual content. So whatever your problem, you probably have a good chance of using E5 as a go-to tool to get started. The other thing that I also mentioned was the instance type. So we have new instance types that work especially well for vector search because they have the right ratio of disk to memory to make the most out of your hardware. And with that, we'll put it all together, or actually here. So we've spoken about vector search. We have the opposite of blue with the whatever embedding model you want to have. So you have your vector search. And then you can combine it with lexical search. So for example, somebody searches for shoes and you want to combine those two. And then you can have with hybrid search, you have this combination potentially with RRF combined to make the most out of those 2 ways of searching. Then you might also include filtering and faceting. So for example, I'm only looking for men's shoes, not women's shoes, not kids' shoes to get those. And maybe I'm only looking for products in a specific price range or that were added in the last year. And what is especially in a more enterprise-y ecosystem important is role-based access control, that you can still filter like who has access to what data, and that you're not limited in any way of what is accessible to who. So you can define roles and then say this specific field is accessible or this document is accessible only to specific roles. And that is kind of like where Elastic thing, where it combines all of those in the center. That's kind of like the idea behind that. We'll dive into a demo. What will be our sample data set for the demo? Forward. What is the quote at this point in the movie?
These are not the droids you're looking
yes,
for.
yeah,
These are not the droids you're looking for. And we'll
I'm like, no,
we'll
Something close to that.
yeah.
we'll build on that.
Do this in a meeting every once in a while.
So
A little hand gesture.
Yeah. Let's see how this goes, and if we have to sacrifice anybody to the demo gods. But I've stood up a fresh cluster that has nothing in it at all. Nothing is configured, so we'll start from scratch. We see how that goes. I have a fallback cluster that has some stuff configured if anything goes wrong. But we'll just open this cluster here, and I'll switch over. So Kevin mentioned that we have these different solutions with observability and security. I will focus only on the search part now. We have this so-called console built in here where you can run commands. This is basically like curl, but kind of like you avoid a lot of the typing, because this is like a curl put my index, and then you would have authentication and everything. But I just say put my index, and this creates your index. So it's like curl, but like a bit of a shorter syntax. It has syntax highlighting, auto-completion. It makes your life a lot easier, but it basically translates to curl. And what is nice, you can even just copy out the curl commands, and in the next version, you will even be able to copy the JavaScript or Python code out from that. So you can just run that as code as well. But you can just keep it very simple and type it in. So let me close this, remove all of this, drop in some code. Is that large enough? Let me make this slightly larger, maybe. We'll start with lexical search because that is where we have come from, and that's kind of like potentially what helps us build up to all of this. So this is running the current stable version. We will take our string. These are not the droids you're looking for. But before that, we'll create the mapping. You don't have to do that up front. I just want to make that step explicit. Otherwise, it would be created for you implicitly. And what I said earlier is like a database just stores data. Elasticsearch indexes data. So it does a bit more of that work up front. And we're defining those steps of what is happening here. So we will have our sample with these are not the droids you're looking for, and it has an HTML tag and an emphasis on the not, and we want to store this. So what we do here in this pipeline is we say, first off, we strip out the HTML because nobody is going to search for the emphasis tag. Next up, we use the standard tokenizer. The standard tokenizer for at least Western languages is pretty simple. It's white spaces, punctuation marks, you break up into individual tokens. Asian languages are much more complicated around that, but Western languages are pretty simple for that. Next up, we lowercase everything because most people don't really type properly uppercase and lowercase when they search. So we lowercase everything, so you have never to care about upper and lowercase in your search again. There might be special scenarios where upper and lowercase make a difference, and then you might not want to not do that. So for example, us or US might make a difference. And you might be careful around that, but let's assume it's simple and we can lowercase everything. Then we remove the so-called stop words. Stop words are just very common words that appear in almost every sentence. They add very little meaning. They would just make our index much larger, and we'll drop them because there is not much value. You would find almost any string with those. So like A and the default list for English is, I think, 33 or so words. It's very short. And then we are using a stemmer. We're using the snowball stemmer. What the stemmer basically does is it reduces a word to the word root. So we don't care about singular, plural anymore. We really care more about the concept of the stem of that word. So we're putting all of that together in, I call it my analyzer. And then I say, my analyzer applies to the field quote. So we'll store one field called quote. And all of these steps happen when I store a document automatically for you. This is all keyword lexical search. Let's create that index. Next up, I will show you what would happen if I would store it. I'm not actually, this underscore analyze only shows you what actually is extracted from our search here. It doesn't do, or it doesn't store anything. So when I take my text, these are not the droids you are looking for. We only get 3 tokens. Droid, you, look, with a couple of things. First off, well, let's see. We have removed the emphasis tag. We have lowercased everything. We have dropped a lot of stop words. These are not all stop words because they are very common. Which is, by the way, an interesting point. This does not understand your text. the not makes quite a big difference, but it is still a stop word. So if there are droids or if there are no droids, that's not the point. Lexical search is really just about matching strings or word stems, basically. Would use it to the word root, so droids becomes droid, you stays you, and looking is reduced down to look. And this is what we basically store here. So here I've just looked at that. And then we have a couple of other things. So we have start and end offset in the string. Why would I need those?
Or how close they are to each other.
Looking for order?
No, that's, for example, if you want to highlight where you match, basically. If you have a long string and you're looking for droid, that you can highlight the droid, but you don't have to reanalyze anything. Like if you have a longer text, it would take some time to reanalyze that and then set the right markers, basically. But we can automatically insert those markers now. So that's again, this trick that search does more work up front, but it will be faster afterwards then. We have alphanumeric. An alternative would be if you define a synonym. So for example, if I search for machine, you wouldn't find droid right now. We could define a synonym for that. We don't here, but we would. Finally, we have the position first, indexed by 0 or 1.
0.
Yes. Like any proper system, it is indexed by 0. And why would I need the position?
The adjacency. Are these words connected to one another?
Yes, if I do a phrase search. So it's a very weird phrase, but if you search for droid you wouldn't have to actually, you basically need to just look at the words that contain droid and you, and then you make sure one has the position n and the other one n+1, and you never have to reanalyze that again. So you can do all of that very fast at query time. That's really the trick that you're trying to do with keyword-based search. But I just spent some time on this because it's like a good foundation to then dive deeper into what vector search is also doing. So I will actually store that these are not the droids you're looking for, and then I'm taking another string, which is no, I am your father, just to have a second string, and we can work with that.
2 different movies.
Yeah. Yes, it's. But by the way, versioning in Star Wars is very weird. So let's not get into that.
Canonical order or?
Will droid match? And if yes, why will it match? So it runs through the same pipeline. So a droid will also be lowercase. There's no more stemming to do, but we have already stemmed the droids up here. So we will have an exact match on a droid. And that is why this is so much faster than if you do a like or I like search in a relational database. You will need to go through the string and do all of these comparisons, whereas here, you basically extract a list of sorted words, and then you just look in that list like, do I have a match for droid? And it has a pointer to the right document, and you return that. And that's what makes search so fast, or keyword search. So this will find my one document, and it gives me back my these are not the droids you're looking for. So much for the lexical or keyword-based search. Now, vector search. There are two types, dense and sparse. And I'll explain sparse in a bit. I'll add the two models to keep it simple. You could run it outside, but I'll just run it on our stack. I'll need to import those. And actually, I should do that because that might take a moment. It will download the model, basically, and add it and make it available. So sometimes this request also times out. It just takes like 30 seconds or 40 seconds or so. So what we're doing here is I'm adding one dense vector model. Those are the two ones that are built into our stack right now. You could add others. That is a bit more cumbersome. I wanted to keep it simple, so we have added the first one. I'll add the second one. Once that has finished, we'll check with get_inference as we check if they are here. You see the APIs are pretty intuitive. So underscore normally it signifies something that is built in or internal to us. And then with put, you just create it. And with get, you can fetch it. And hopefully this worked. And you can see we have those two models, E5 and L, so we have those created. And now I will take my Star Wars index and I make it a semantic Star Wars index. And we create the same thing for the keyword-based search. The only thing that we're adding now here is that I'm creating that semantic text field for my sparse and my dense vector representation. And I basically copy that quote field into those other two. So I will take the same string into all three. But then when I store a document, I only need to provide that quote string once, and it will be indexed multiple times so I can search across them. But that's also coming back to your point that you probably want to store it in multiple formats to make search more powerful. So let's create that mapping. That worked. And now I'm saying, take all the documents from the Star Wars index. I mean, it's only 2. But this is what you would normally do if you change anything in your mapping or you change the model behind it. You might have to re-index documents that they're regenerated in its full form to be searchable again. Because normally what you need to have is that however you store something, you need to search it the same way. Otherwise, the two don't match and you wouldn't have any matches. That's also why an older schema is not really something that is easy to do in Elasticsearch. You can always add new columns, for example, or fields, but you cannot really change existing ones because it would break that contract that things need to be the same to be searchable. There's just the trade-off of doing all of this work upfront when you store data. So now I'll use ELSER, and you will see how ELSER works when I run this query. And I'm searching for robot, and you can see it finds one document, and it finds that these are not the droids that you're looking for. And it has these two representations. So it has the dense vector representation, which is long, and we'll just scroll through that. That's the kind of boring one. Oops.
Now, that's the dense representation of just the quote?
Yes.
Okay.
That's what you have to, but that's also why it's expensive in terms of memory.
Right, right. I'm just trying to understand exactly what's being encapsulated.
Yes, so
there.
These are not the droids you're looking for. Was that long?
Was right now, but
384 dimensions.
Right, but that was. So this is the strip down to the 3 tokens, or this is the whole quote?
No, this is just this is the full string. This analysis is just for the keyword-based search.
Right. Okay.
So this is really taking, these are not the droids you're looking for, and this is the dense vector representation of that. So this is the tail end of the dense vector representation.
It's taking the embedding version of that.
Yes.
And that's whatever your embedding is, 384, 4096, or 25.
Yeah. That's why don't do more dimensions than you have to, because it will be expensive to store, but also it's more expensive at query time.
Yep.
And then we have ELSER, which is, this is based on like the open source or paper-based model is called Splade, and ELSER is like our custom improvement of that. What this does is it's a query expansion. So it takes, these are not the droids you're looking for, and it's not really like synonyms, but it's like it expands it to these tokens, and the hashtag is like a wildcard, and then a numeric value of like how high the match or how good the match is. So it does this automatic expansion, and it somehow figures out that, for example, Galaxy is high here. I'm not sure why Doctor, but maybe it's from Doctor Who or something like that. But it is also trained on data, and then gives you this expansion. And when you do a search, it expands as well and tries to find the matching words with the highest numeric values. And this is how you match. So you don't have to provide like the synonym to say like a droid is a robot, but it will automatically expand that for you. But it didn't find no, I am your father, because that didn't have a lot in common with that. So it avoids that vocabulary mismatch problem here. We can also search for, now I'm using the E5 model, the dense vector representation. By the way, to make the reading a bit easier, I only return the quote and not the dense vector and the sparse vector, because that's just a pain to read and scroll through. By the way, the ELSER representation normally expands to 50 to 70 terms. Also reasonably long. With all kinds of weird words, like we had to, I think, exclude some bad words and stuff like that. So things that you learn.
About that.
Yeah, it's. I think at some point we discovered that when ELSER only works for English, when you give it German text, because it has probably learned it from movies, it will always say Nazi. Just a slightly weird inference, but that's what models have been trained for movies or whatever data we have. So the dense vector representation will find both documents, and no, I am your father is closer for dad than the other one. But here, this is, by the way, something to note, because in the vector space model, everything is basically related to everything. it might be further away, but it's still at some distance. So there is like, you probably need to have, either you have a lot of good matches and then these other ones will fall below the fold or whatever you retrieve. But you will always have a match to some degree with dense vectors. So just be aware of that. There is no...
Which is how hallucinations work.
Which might be part of, like, we'll get to, we're 23 minutes, yes, we'll get to that in a little bit and see how things are going.
Say that, haven't you?
And just to show you what we can do here as well, we can combine those. So here, I'm just doing manual boosting, not RRF, because we've had those examples before. But here I'm saying, like, search for Elster, and this has a boost of 1, but I have a keyword search, and that's 3 times as relevant, for example. And I'm searching for Android. This one will not match because there's no Android match, but Elster will actually match that. And I think it will even match on the second one because I don't know why. I didn't check in detail which one of the words has some overlap. But you can see the relevance here is, this one is much higher than the other one, whereas this is very, very faint. It just casts a very wide net to retrieve what